Okay, so I won't get through everything, and hopefully, if anybody wants to reach me with any questions, that's my email address. So I'm at the National High Magnetic Field Lab in the United States, and I'm just delighted to be here. I really, really wish I were in Bochum. I've been to this conference for years, and I love it, and it's very hard to do this by Zoom, and I miss all you guys. So why do I have the title of this talk? The title of this talk is really just to be interesting and to bring people in to really believe that quantum materials is not any less fundamental than any other area of physics. And I've been doing quantum materials and novel superconductors for many, many, many years. And it's sort of my view from 35,000 feet up in an airplane. And in quantum materials, there are dozens and dozens of unsolved questions that are no less fundamental than gravity and dark energy. But I like to bring in the unification. And again, this is an overview. You can actually make these analogies work a little better if you spend some time on it. But I'm going to compare this a little bit to cosmology just because it's popular and it works. So if you have colliding black holes, the gravity waves are spread entirely across the universe at 10 to the 26 meters, and the energy is 10 to the 49 watts, more than all of the light emitted in the universe at a given time. Quantum materials, we look at little electron clumps quite often, as we're listening to at this conference. And for instance, there's a cartoon of electronic mimeticity. The length scale is about 10 to the minus 10 meters, 10 to the minus 21 watts. So the difference in length and power is about 10 to the 36 or 10 to the 17. And a lot of the same mathematics is used in both those areas. So this is kind of a fun look at. Now, I'll give an introduction to the Magnet Lab. I won't spend much time on, I left this off here, but I won't spend much time on what a superconductor is or unsolved quantum materials. I'll mention them, and then I'll do a fun analogy. And what I don't have in this outline here is I'm going to give you a short talk on our work on cerium cobalt indium 5, the heavy fermion superconductor, and how we have a huge amount of evidence that the pairing mechanism is due to Kondo scattering. And I'd be happy to talk about that later. So this is the National High Magnetic Field Laboratory. We have 3 campuses. I have pictures here from our campus in Tallahassee, Florida. You can't really understand the scale unless you were there. All I can tell you is that if I go from my office to my laboratory, it's a long walk. And we have many facilities here. And one of the facilities is the DC facility, where we have the largest DC magnet in the world at 45 Tesla. And here's a 21 Tesla NMR, MRI magnet. I will show you some more later. At University of Florida, about a 3-hour drive from Tallahassee, we have 2 user facilities. One is advanced magnetic resonance imaging and spectroscopy, where we do MRI on living objects and living things up to 21.1 Tesla, and the high B/T facility that can go to millikelvin for 6 weeks at 17 Tesla. So the fields aren't as high, but no one can get to those fields at such a low temperature. In Los Alamos, we have the pulse field facility where we can go at 101 pulse magnet. This is the largest field in a non-destructive magnet. And to give you an idea, here's the generator, and there's a normal sized human being standing there. It's really vast, and it's a lot of fun to visit. So we have, I'm missing something here, but that's okay. These are some of the records that we've broken. And I'm going to skip this one because I pulled one out for another talk. Yes, it's been one of those times. But in 2018, what I'm not showing here is that we commissioned a 32 Tesla all superconducting magnet as a user facility. And this is very important because if it's all superconducting, then you don't have to have the water cooling, and you can do much quieter measurements. And it's being used for all kinds of very quiet measurements right now. And we're hoping to do imaging in that magnet at some point. Oh, no, that was okay. And that was another one that we had. This is the 45.5 T high temperature superconducting test coil. So it's small, but it's a proof that the 32 T all superconducting magnet, that's the one here, sorry about that. It was proof that we can go higher. We're commissioned to build a 40 Tesla all superconducting magnet And this one here is a small test core that went to 45.5 Tesla. It all has to do with what's the insert and what's the outsert. In all of these super high Tesla superconducting magnets, you have to use high temperature superconductors. Both these use Repco tapes, not because of the temperature of the critical temperature, but because at low temperature, they're the only superconductors that can take the high fields. Now the Mag Lab holds many, many users, and here we show people going to Gainesville, Tallahassee, and Los Alamos, and that's our Delta Airlines map to show where people come from all over, in fact, all over the world. We get people from all over Europe, including Geneva and Wuhan, that have their own Hefe that have, this is just to tell you the scale of the place, that we have people, 300 institutions throughout the world in 2019. And I also want to point out that 1/4 to 1/3 of all principal investigators are first-time users to the Magnet Lab. So if you go online and pick out an experiment, a magnet you want to do, the Mag Lab scientists will help you write a proposal, and it's free to use. And if you've never used high field magnets before, the faculty at our user facilities will certainly help you out. So you're welcome to come. The major themes of the Magnet Lab are materials, energy, and life. Now I'll just give a few quick examples here. Here's an example that's a little bit older now, so I won't go into it, but it's how this is the high temperature cuprate and how you can put in high fields and break the superconductivity in the superconducting dome. And one of the measurements from a few years ago showed that there are probably 2 quantum phase transitions under there, because using quantum oscillations, we can show that the mass on the Fermi surface actually starts diverging as you go into the superconducting dome. But here we go. Here's a measurement that was really fun to find in 2019. And this was what we call the Lazarus superconductor. The group discovered that in this heavy fermion material, uranium tellurium-2, so this is angle and this is field. And here we have a low field, it's superconducting. If you increase the field, of course, you break the superconductivity, and it's normal in the white phases here. But in this funny angle here, if you go above 35 Tesla to just above 60 Tesla, you find a new reentrant superconductor. These data were taken both at the DC facility in Tallahassee and the Pulse facility in Los Alamos, but no one ever expected anything like this. And it's completely new, and later measurements show that there looks like there's some texture to this phase. Another example which I like to show is ion cyclotron resonance. This is a mass spectrometer on steroids. No one could come in within an order of magnitude of this kind of resolution. It was developed to study the most complex fluid on the planet, which is oil. And this is the kind of resolution that we can see. If you're doing time of flight spectroscopy, this is your resolution. In this ion cyclotron resonance, your resolution is within about an electron mass difference. You can resolve an electron mass difference. And what this is applied to is it was developed for petroleomics. And in petroleomics, an example is if BP and Exxon drill wells in the Gulf of Mexico, it costs them each $1 billion. And if they want to find out if they hit the same oil reserve or not, we can tell them. We also do forensics. If there is an oil spill, we can tell exactly from wellhead it came from. That's because we have that kind of extreme. There is a fingerprint of every well. We've used it quite often for proteomics. My favorite example is the P53 protein, which many of you know that the protein folding determines its functionality. In P53, we can classify its folding through an HD exchange to know if it's malignant or non-malignant. And you can determine protein makeups and amyloids and all kinds of stuff. I have one slide to talk about climate change. The second most complex fluid on the planet is dissolved organic carbon. And so you really need this machine to understand what's going on the built planet and climate change. And I'll just show a couple pictures here. We take measurements in the Arctic, and we could measure how the dissolved organic carbon changes with time and location, and track climate change in the Arctic. That's just one of many, many examples. One that I'm really impressed with is measuring the runoff of asphalt and other kinds of surfaces from the built planet. So we can tell you if it's going to be water insoluble carbon or soluble carbon. And no one else can tell this. And it actually is more of the shape of the carbon chains. Again, we have this resolution. The other thing that I wanted to point out, if anyone's interested, is that we could measure these PFAS or the forever chemicals, and we can tell if people are being in compliance of not using the forever polymers on what they're building. And so it'll be interesting for regulation to keep the planet cleaner in the future. One example of life is high resolution MRI. So probably most of us had MRIs, and in the commercial MRI, you go in and this is 2 to 4 Tesla. Now this is an example of a single cell image. You have about 1 millimeter diameter. If you're imaging like we normally do when we do MRI in a hospital, you image on the hydrogen. And then we get about a 1 millimeter diameter. But if you image at the hydrogen on 21 Tesla, you get to microns resolution. However, as you know, when you are taking an MRI, you have a resonance condition between the field strength and the applied RF field. And measuring at 21 Tesla, the resonance frequency for hydrogen is really not good. It's not as bad as being inside of a microwave oven, but it's not that healthy. So we typically use 21 Tesla either to look at non-living things, like here's the skeleton of a frog, or we can look at other kinds of elements. So we call that unlocking the periodic table. Here's one of many, many examples of looking at sodium. So here is a rat. I've learned when I got to the magnet lab, you can actually buy a rat with brain cancer. So what we have here is in sodium imaging a tumor inside of a rat brain. By the way, the rats are perfectly fine. The RF frequency is low. It's low because sodium is much heavier than hydrogen, and it just has much lower resolution, but you can see the sodium. Now, it turns out that as cells are dying, they uptake cancer. We're not really sure why. We have some idea, but it doesn't matter. We just know this. So what you do is you give the rat chemotherapy, wait 4 days, and image again. You may have to do this several times, but if all of a sudden the sodium lights up, that tells you that the cells in the tumor are uptaking sodium, so are probably dying, and that gives you confidence that that regime of chemotherapy might be working. It's in the prototype stage, and it's only at the size to do rats, but it's a very promising technique. Now I'm going to go on to spend a little bit of time sort of having fun with the dark energy part, and you have all seen this. I'm at a superconductivity conference. And this is just to remind you all that I have only plotted a small fraction of unconventional superconductors. The conventional ones I have in red. I don't have the organics. There's all kinds of things that I'm missing here, but these are the Coop rate. This is the superconducting transition temperature, and this is the year of discovery. And of course, this is the discovery of the highest TC that year. And we're also all familiar with this domed plot here. Now, I define that in unconventional in conventional superconductors like niobium, niobium-3 germanium, niobium titanium, above TC, you basically have a weakly correlated, basically a Fermi liquid, and below that temperature, you have a BCS electron-phonon coupled superconductor. I classify the unconventional superconductors as having this phase diagram. It's just a cartoon that I took. We all have our own cartoons of these things. And what's fundamentally different is that in almost all these unconventional superconductors, because nothing's everything in quantum mechanics, on one side you have typically another kind of strange metal. You can have an antiferromagnetic insulator or an antiferromagnetic metal. On the other side, which is the overdoped or the high pressure side, you can go back into a Fermi liquid. As they meet in the center, as we're all aware of, there's the superconducting dome. The superconducting dome can have all kinds of, it's just the superconductor. Let me just point out the way I look at this, okay? When we look at a Fermi liquid, like a conventional superconductor above TC or the overdoped high pressure side of this phase diagram, there are electronic structure techniques that can give us the optical transport and thermodynamic properties, that we can calculate. When we go under the dome here, when it's superconductors, up to now, all data support that all superconductors exhibit Cooper pairing. If they exhibit Cooper pairing, you can still calculate the optical transport and thermodynamic properties. You can use the Begali-Bogdazian equations. It's a little more difficult, but you can calculate these properties. What I'm calling the unsolved quantum matter is this area up here that we've all heard about in this conference: the electronic pneumaticity, the extra, the heavy, the 500 times free electron mass and the heavy fermions, stripes, pseudogap, etc. So my definition is that we are finding an unconventional superconductors that is not necessarily because, you don't always have in unconventional superconductors, you can have S plus minus. And the old definition of unconventional superconductors was that the superconducting phase was a lower symmetry than the underlying lattice, the superconducting order parameter. That's not necessarily the case, for instance, in S plus minus. But in all these materials at some temperature, we find that the electronic fluid above the temperature of the superconducting phase, that electronic fluid breaks the symmetry of the underlying lattice, for instance, in the case of the pneumatic phases. Now, just to show that we've all seen this before, how ubiquitous this is, this is when this was first studied, but with Steglish and Langeres and a heavy fermion superconductor. There's the superconducting dome, the Coop rates. Here's some data from my laboratory that we have way up here. We have pneumaticity and et cetera, et cetera. And so we've all seen these before. We don't have to go into that. I find it most exciting to discover, to study these unconventional electronic phases up here. Because if you think about it, and I'm not the first person to say this, is that you have a dome, so you have lower TC on the right side when it's a Fermi liquid, when it's or weakly correlated. When it's strongly correlated on the other side of the dome, TC is lower, and in the center, it's higher. So it looks like these high correlations are bad for superconductivity, these strong electronic correlations, but you don't get high temperature superconductivity without it. So it's some sort of interplay between the correlations above the dome and into superconductivity. And what is that delicate balance? So just to remind you, as I said before, I don't want to spend a lot of time on this, but here's an example of the electronic pneumaticity, which we've measured way up to 175 degrees in this iron-based superconductor. People measure stripes, et cetera, et cetera. This is to be the overview before I get into a little bit of data, and just to give you the, oh good, I think I'm doing okay, 10:15 to 11, okay. So I guess the general feel that I want to give, as this is a general talk until I get into the details, is that we have, I put this as many, many, many kinds of unconventional superconductors, the cuprates, the iron-based, the heavy fermions, organics, et cetera, and they're all a little different. They all may exhibit the same kind of phase diagram, but as soon as you get into the details, they're all quite different. Each family is quite different from each other. And what's happened through the years is people have developed all kinds of intriguing measurement techniques, scanning, tunneling microscopy, what they've been able to do with ARPAS and resonant inelastic X-ray scattering, et cetera, et cetera. Here's an example of quantum oscillations that was done several years ago in the Magnet Lab, where you map out the Fermi surface, and this would not have been possible without the much higher quality growth. It's been like a revolution in growth capabilities of these materials. So without, you can pick out your favorite technique of measurement. Growth has seen transformation, and computation has also seen revolutions in what can be done. So it's my argument that all these things together may help us understand the many, many, many quantum materials that we don't understand. So I've already mentioned this about what is unsolved and solved quantum materials. So just to remind you, a conventional superconductor is a Fermi liquid above TC, and below TC, it's understood superconducting Cooper pairs, and it's electron phonon BCS electron phonon mediated. So those are solved problems. In these unconventional superconductors, the far right side is a Fermi liquid, under the dome is a superconductor Cooper pairs. We don't necessarily know how they're paired, but they're Cooper pairs. And up here, there's all kinds of things we can't describe. So I consider the big question in quantum, in these highly correlated systems, is what's going on in these weird phases, of which there are so many of them above the dome. So here's my analogy, and then I'll get into some technical stuff. This came to me I was at a Kavli lecture where Kip Thorne was giving a talk, and he put this picture up that we've all seen many times, which is a distortion in the space-time continuum of the sun and the earth. And the sun, of course, has a higher mass and distorts the space-time continuum a lot more than the earth does. And so, so I saw this and I thought, in BCS, you're also distorting the background. When the electron goes through, you distort the phonon background, and that's the basis of pairing in a BCS electron phonon mediated superconductor. There must be an analogy there. So at that meeting, most of my friends told me I completely lost my mind, which could have been true. But then I thought about it, and I left that meeting, and I actually got the analogy done within about 36 hours when I had to give a talk at an applied superconductivity meeting. So this is part of the analogy, and you could take it further if you want. But I want to remind you of the gravity wave detector LIGO. And I mentioned two black holes colliding. This was an amazing telescope or microscope on the universe. The energy that they detected was more than the combined power of all light radiated by all the stars in the universe. Yet the detector moved less than the width of a proton. In my opinion, the National Science Foundation spent $1 billion over 20 years, and it was the best $1 billion they ever spent. It totally changed the way we looked at the universe. On top of that, which I always want to stress, and I'll repeat it again in the next slide, is that for the first time with LIGO and all the telescopes that came afterwards to detect gravity waves, for the first time, we can look at the universe besides just measuring mass or light, a whole new way to look at the universe, which I consider important, and so do most people, okay? And now the other thing is that we don't have a set of gravity wave detectors, but we have many kinds of quantum detectors. I listed those whole list of letters, et cetera, STM, point contact spectroscopy, ARPAS, and we've also increased our ability to grow crystals and computation. So those are many, many, many facets of LIGO, because we have so many quantum materials. Just to recap the analogy, Mr. Newton decided 1/r² worked for gravity, and it worked for a very long time. But there were a few problems, like immediate action at a distance, instantaneous action at a distance. And Mr. Einstein scratched his head and said, there's a few problems here. And he pointed some other things like the retrogradation of the perihelion of Mercury. Newton wasn't working. So he came up with this amazing theory, the general theory of relativity, which showed that the microscopic theory of gravity was actually a distortion in the space-time continuum. The question we have now is, can this new way, so it's been measured, and there was a new way to look at the universe that was invented and developed to look for these gravity waves. They were discovered. Can this new kind of telescope look at the universe and tell us how to find the most unsolved problems in cosmology, dark energy, dark matter? The analogy here is that Mr. Fermi showed us pretty much how to make a Fermi liquid. And we know when it's put into a lattice, it kind of changes a little bit, and we can calculate that. We know that Fermi liquid theory didn't work for superconductors. And Bardeen, Cooper, and Schrieffer actually were able to find a way that worked. But it didn't work for all superconductors, and it certainly didn't work. And the mechanism of pairing didn't work for all superconductors. And we don't have any theories that completely describe all these other forms of quantum matter, like pseudogap, pneumaticity, et cetera, et cetera. How are we going to get there? And so this is the analogy, then I'll move on to more technical stuff. Two great unsolved problems in physics. In gravity, the Newtonian classical view is that forces between objects are derived from mass and their positions in the universe. In quantum matter, the properties are derived from What's the object? The crystal atoms and their position in the lattice. In the Einstein general theory of relativity, the masses create distortions in the background, which happens to be the space-time continuum. In the BCS electron phonon theory of superconductivity, the electrons create distortions in the background. By the way, this is one of 2 solved quantum materials, highly correlated problems that I know of. And so there's a lot that we need to be working on this. Unsolved, dark energy and dark matter, and all those correlated electron states that we don't understand. I'm going to move on now because I think I have 5 or 10 minutes. Is that right? Haluk, you look like you're okay. Just start yelling if I am going over, okay? I think I'm keeping on time. So now I'm going to go to something that's a lot more technical. So we're doing a big jump, and this is something that's in Physical Review B in 2021, and we're pretty excited about it. And I'll go on here. And so the introduction motivation is we've been looking in cerium cobalt indium-5, a heavy fermion superconductor, for many, many years. And it's got non-Fermi liquid behaviors, as they all do. TC is 2.3 K, and it has some funny jumps in the specific heat and the susceptibility. And what we do know is that the heavy electrons are the ones that form the Cooper pairs. Just to remind you, the T star is about 45 degrees in this material. We looked at this a long time ago, and people have studied this and discovered that they were D-wave due to thermodynamic measurements. We did some point contact spectroscopy a bunch of years ago, and we were able to show by the shape of the quasi-particle scattering in this measurement that we could locate the nodes, dx squared minus y squared. There are STM measurements that are listed on the bottom that also show that this is a dx squared minus y squared symmetry order parameter in the superconducting state. So we're in agreement of that. So I'm not going to go into this Q phase. Just want to tell you about the experiment. We've done this kind of experiments a lot. The samples are great. We define things. After a lot of work, after almost a year of work, you can find a way that they're reproducible. So what we do is all these experiments have lead counter electrodes. So they're SIS at low temperature. So this is an example of a lead insulator, cerium cobalt indium-5 at low temperature junction, and we can see the lead phonons. It looks great. If we blow up the central area here, we have the delta 1 plus delta 2 and the delta lead. And so this is exactly what you expect. You don't see the delta 1 minus delta 2, and we'll see is that there's still a lot of density of states in this dx squared minus y squared superconductor around zero bias, so you're just not going to see it. But this shows that these are very, very high quality junctions. So now that we know we have high quality junctions and they are reproducible, the next thing you do is put a field on it to drive the lead normal. And then you're looking at an SIN junction where S is the cerium cobalt indium-5 and N is the lead driven normal. And we just put on 2 kilogauss. I think I'm going to just go right into the meat of the material. Let's start with the temperature dependence of the junctions. So this is in agreement with what other people have seen, and those other 2 STM papers that I referenced before, 3 that I referenced before, they see the same thing. That is preform pairs above TC. So what we have here are, this is the current voltage with the only field is 0.2 Tesla, 20 kilogauss, which is very, very low for cerium cobalt indium-5. You need several Tesla to drive these things to get HC2. And all we want to show here is if we look at these color plots, is that this line here is where TC is, okay? And if we go up in temperature, going up in temperature here, we see that there's stuff going on above TC. And without spending a lot of time, we're in agreement with previous measurements that shows that there is pair potential above TC, and we have identified those that are definitely preformed pairs. That's a little detail here. Now I want to talk about the magnetic evolution. And in the magnetic evolution, we are now all at low temperature. Here, this one, in this orientation, 001, and 100. So the 001 is coming down on the C-axis. The 100 is coming in like in the A-axis. And we can, mount these and polish them down. And then this is the 110, of course, is the nodal direction for a dx squared minus y squared superconductor. What do we see here? If we look at the 001 oriented, and again, the only field on here is about 2 kilogauss, start out that way at that lower one just to drive the lead normal. We stay at low temperature, in this case, 0.4 millik. I'm sorry, that's not 0.4 millik, that's 0.4 K, that's probably 400 millik. And what we do is we increase the field. And as we increase the field, just have a look here, we see the superconducting gap. As we're increasing the field, we start losing those little resonance peaks, and we just get this dip in the center that increases with increasing field. That's also true in the 100 orientation. This is the superconducting gap. And as we raise the field, we notice that it starts looking like a superconductor, and it starts looking like some other gap comes in here. Now, I want to point out in both these things that this gap persists, this gap-like feature here persists above HC2. HC2 in the 100 orientation, okay, is 12 Tesla, so that's here. And look what's going on in 14 and 18 Tesla. In this orientation here, HC2 is about 5 Tesla. And look where we are at 6, 9, and 11, and 14 Tesla. There can't be any superconductivity in there. So there's some gap in there that's increasing with increasing field. This is a more complicated to understand in the nodal direction. All we can tell you is that we have an understanding, I won't have time to explain it here, is that we do see this splitting more quickly with applied field. And that's probably because there's very few Cooper pairs in that direction anyhow, because that's the nodal direction. Now, I want to point out something in this magnetic evolution. We showed increased gap formation when you go above. So right now, everything in gray is what I just showed you, okay? These data were all taken at low temperature, and this is the correct temperature listed here, and as you raise the field, we see the superconducting gap go away, and smoothly another gap, we call it a FIG, a field-induced gap, starts coming in. Now look at these to the right here. You haven't seen these data before. These are done at 4K. TC of this material is 2.3 K, so we're above the superconducting transition temperature. But we're in the area where there's pre-formed pairs. Both our group says that, and those other groups that I mentioned earlier say there's pre-formed pairs. And what do we see? As we increase the field, we see there's no gap, but we see some kind of a field-induced gap coming in. And that's also true. We see a splitting coming in the 110 direction. Now, hold that thought. When you're in the pre-formed pair range, when you're below TC, when you have coherent pairs or incoherent pairs, increased field gives you a field-induced gap that grows with applied field to the highest fields measured. If we go above that temperature, these are data taken at 10 and 15 K. If we're above the preformed pair temperature, there is no field-induced gap. In other words, you need to have some kind of Cooper pairs there, either preformed pairs or coherent pairs, to get a high field-induced gap, okay? And that's just repeating it, and there's some data that we plotted up, and it gives you the peak position, et cetera. So our conclusion, which I can discuss in more detail, and we can argue because I've been doing condo scattering and tunneling for years, but this really looks like a 2-channel condo scattering. And a candidate is a composite D-wave pairing, but definitely it looks like a bulk example of what has seen in tunneling before, which is 2-channel condo scattering in an interface. We believe we're seeing it in the bulk. So our conclusions are many families of unsolved quantum materials, many new and innovative theoretical tools. Will they help us understand all these kinds of quantum materials? That's what we're all here for. And my takeaway is that a pairing due to condo scattering in the heavy Fairman superconductor, cerium cobalt indium 5, and I'm happy to take questions. Thank you. Should I stop sharing?
Yes, thank you very much, Laura. Is there any question?
Thank you for a nice presentation. So could you refer to the Volovik book, View Universe in Helium Droplet? So he describes some analogy of helium A and B with cosmology, and elementary particle physics, and somehow he accounts for some of your analogy between pairing and space general relativity. However, in case of his considerations, there is no crystal lattice, so possibly this metric of space can be much more tuned than in your case. So can you make some comment on that?
To be honest, you're a little over my head. I've certainly looked at Bolovik's work. So as far as getting down to the actual microscopic analogy, I really can't do that. I've had some people send me information that they could. Right now, this is really to just get a feeling that there is some distortion in the background. And now I do not believe that this distortion in the background of electron-phonon scattering is the only explanation for superconductivity. We already know places it doesn't work. So this is a difficult analogy because we're not just looking for a gravity wave. We're looking for what explains pneumaticity, heavy electrons, et cetera, et cetera. So this is just one piece of an analogy to help us understand. And frankly, one of the take-home messages is that we're not building Geneva, CERN to find a Higgs boson. We're not building LIGO to find gravity waves. We have this whole suite of telescopes, which are the measurement techniques, crystal growth techniques, and computation techniques to find our dozens and dozens, understand our dozens and dozens of kinds of quantum materials, of highly correlated materials. So that's really what the analogy is about.
Wow, very nice talk. Thank you. Could you give a bit
Just
more
see the back of your head. Is that Catherine?
Yes, Catherine. Yeah.
Oh, it's so nice to turn around so I can see your face. Hi.
Hi. So we are missing you here, and we are very happy to hear that you got a job close to Joe Biden. I think it's good for everybody. So I wanted to ask you to give a bit more explanations on this two-channel condo. It's not very clear to me how it's linked with your observation of preform pairs. Could you just give some precisions on that?
Okay, so you're very familiar with this, Catherine, which is a single impurity condo scattering. And this is what we have here is that this was measured like crazy. And Shannon Rowell did this a long time ago. And the way they describe this was that there's some kind of magnetic impurity in the interface, either near or in the barrier in planar tunneling. And as they applied a magnetic field, they saw the splitting. The explanation was given by Anderson and Applebaum here. And what we have here is that if you have, and so this actually was then argued as it's a different kind of two-channel that was described earlier. So if you have elastic scattering, this is what the conductance looks like. Let's go here because I'll take too long otherwise. So here is what we have: conductance in an NIN junction with no magnetic impurities. And then what you have here, even if you apply a field, you have Ohm's law. Now, if you put a magnetic impurity in the interface or near the interface, then you open up a new channel for scattering across the junction. And what happens then is that you have an easier way for the electrons to get across. When you give them enough energy that they can flip the spin in or near the barrier, they have a new channel to get across. And then you get an increased conductance when you increase that energy of the bias. And so you get a splitting here. It looks like a splitting, but it's actually increased conductance outside of the Zeeman splitting. And that increases linearly with field. And just to remind you, if you have, this is what was called two channel in those days, you have an interference. You have a tunneling electron coming through that has a constructive interference with a tunneling electron that spin flips, and you can get a constructive interference and get this condo peak here. And with the applied field, it'll split, and this is what it looks like. This has nothing to do with superconductivity. This is condo scattering and Zeeman splitting. So I guess one thing I want to show you that was surprising in our data, which I jumped over very quickly, is that the splitting occurs linearly with field. Up to 18 Tesla that we've measured, the splitting was absolutely linear. And that's why we went to this condo scattering, because Zeeman splitting is linear with field. So this is our cartoon. The idea is that you have a general single impurity condo scattering. Here's an electron scattering. And if you have like a Kramer's doublet down at the F level, and then you'll have to talk to Rebecca Flint and Pierce Coleman for the real details, because I can't really get there from here. But now, because you have your doublet, two separate electrons can scatter on the single F level, can condo scatter on the single F level. And then you have, this two-channel condo model. Now let's apply a field. As you apply a field, you start breaking this degeneracy. Okay, so this Kramer's doublet will start to split, and now you go back to the single impurity condo. You don't have that degeneracy anymore, and that splitting should grow linearly since it's Zeeman splitting. And so what's interesting is that unless you have some kind of this pairing, whether it's coherent or incoherent, you don't see this condo scattering, this linear increase of the gap with applied field. Did that help at all? Here are the references to their papers.
Thank you.
There is a question online from Abdul Hassan Nian.
Hi, can you hear me?
Yes.
All right. Thank you very much for a wonderful talk. I was wondering about the gap at high field. How are you considering doing STM to study the spatial dependence and whether this might be related to pseudo gap or something like that? It looks like it's not competing with superconductivity as you show. It might be a prerequisite for superconductivity. But the spatial dependence would be actually interesting. Just to see where exactly coming from the sample and whether it's proof elite or not.
That is a great question, and I wish we could do that. One of the advantages of planar tunneling is that the junctions are robust. We can look at them in different fields. It's easy to go up to 18 Tesla. Not easy, but it takes a lot of work and a lot of working on the junctions, but it's possible to stick it in different fields, look at it in different orientations, change the orientation of the field, and do junctions at different faces up to 18 Tesla that we've done. We're trying to go to 45 Tesla, but we haven't run the hybrid in a while. We're just starting to run it again. I wish you could do these kind of measurements in STM. I think it would be really important, because what we can do is we go down with the football field of a junction. It may be micron sizes, but we don't have spatial resolution. We have some momentum resolution, as you can see, but we don't have spatial resolution. So right now, this is the best we can do. And if someone's interested in going to high field with STM, that would be great. I'd love to see them try to do that. Now that we have the new 32 Tesla all superconducting magnet that's very, very quiet, I think it would still be almost impossible. We've worked with other experts in STM. It might still be impossible to do STM at these high fields, but I think we should not give up on that.
That's right. Thank you. Thank you so much.
Thank you.
Another question is Efrat Shimshoni.
Hi, Efrat.
Hi. Thank you for a very nice talk. I have actually two questions. One is concerning, you mentioned that you have a free form pairs and the heavy fermions, where these are heavy electrons or heavy fermions that are paired. What is the experimental indication for that? I mean, do you have anything that can hint of what is the mass of the?
It's about 85. M star is about 85, the free electron mass, um, uh, uh, up here. And for looking at this, when they start getting heavy, they're about 85. M star is about 85, the free electron mass. And from looking at the specific heat, we can see by this value here, the electrons that go into the superconducting phase from the specific heat are the heavy electrons. If there's a better expert on specific heat, if you want to break in, I would appreciate it.
Okay, I have another short question. You mentioned earlier in the talk the Lazarus superconductor. So, is there any theoretical proposal for that?
I don't think so yet. In fact, next week, it's in Santa Fe, and I can't get there from here, but I want to advertise that there is a meeting in Santa Fe. I think it's Thursday, Friday, and Saturday. I'm not sure, but take a look. Peter Hirschfeld is one of the co-chairs, and they're going to be focusing on this, and I'm going to be joining by Zoom. I wish I could get to Santa Fe too, but my life isn't allowing that. So I guess I would say with my schedule right now, I don't know all the details. Later measurements, as I've mentioned, indicated that it might have a, there might be some texture to it. So people are saying, can you use this for quantum computing and stuff like that? But you can't give a talk on condensed matter without using the words quantum computing anymore. But there's a lot of papers that have come out recently, and so I just strongly recommend that you maybe attend that conference. It's like $50 to attend by Zoom. So, and if you want to know, and Fred, I'll send you the link and I'll send you some other papers. Okay.
Okay, thank you. So I have to leave actually. So
it's great to see you. Let's catch up sometime.
Yeah. Okay. Bye-bye.
Bye-bye.
Yeah. Last question from Aliganjar.
Hi, Ali. It's nice to hear your voice.
My mind is a little mixed up with quantum technologies, materials, quantum technologies. I need to know your vision about quantum materials, range of quantum materials or technologies, let's say, in future. I mean, what do you expect that will happen within the next 10 years? Because in European Union and in China, in USA, there are big fundings are being allocated for quantum technologies. And what would be the share of superconducting materials, let's say, in this fast developing area?
Thank you, Ali, for always asking such easy questions. No, that's really a great question. Of course, my view will be my opinion. One of the things why we need to be studying all of these materials is because we don't know what the next qubit's going to be. And considering that cold atoms are still in the running means that whether it's, we can look at any of a host of materials that you're discussing here at your meeting, including unconventional superconductors, including conventional superconductors, including graphene, including quantum Hall edge states and things like that. So all those things are in the running. So we have to keep studying novel materials to figure out what's going on there. We need to put research into there. So I think what we're looking at, and is basically the second quantum revolution. What we're doing here is trying to develop technology, the science and the technology So just like all of our cell phones are run by, and all of our technology and our entire society, to a large extent, is run by quantum mechanics, right? And that was, goes back 100 years, and that's understanding and controlling the quantum. I look at, and I'm not the first one to have said this, it's been said by many people, is that this new second quantum revolution is about controlling the phase of the quantum. And it's so much more powerful. And you're right, China's put a huge amount of money into it. The UK, the EU, and the United States is getting on the same bandwagon. Why? Because it's very exciting and it's very important, and it's where it has to take us. Things like sensing and, well, you've seen all these things, but it's very important. And so my guess, within the next few years, we will have come up with several really great qubits that are manufacturable and scalable. And at the same time, people are working on the mathematics, the data analysis, all that, that has to go in there. And so I actually see these things all coming together and changing the way we communicate and we sense things, and what other kinds of applications will occur. But those won't happen unless we have a much better understanding of how to design and create such materials and how to turn them into useful devices.
Okay. Thank you very much again. Your presentation. Thank you, Laura.
Thank you very much. It was a pleasure to be here. I appreciate it.